This is the fifth lecture on tensor algebra. In the last class, last lecture, we have introduced the tensor of rank 2 tensor, and we defined quantavariant tensor of rank 2, covariant tensor of rank 2, and finally we defined mixed tensor of rank 2. And we have also discussed about the fact that if we have a tensor which is to rank 2 tensor which is symmetric about either two covariant indices or two contravariant indices, then this symmetry property is retained under coordinate transformation. But if the mixed tensor or a tensor be symmetric in one coordinate system with respect to interchange of one covariant and other contravariant indices, then this symmetry property is in general not carried over to other coordinate system. This is an accidental symmetry which is observed only in one coordinate system, and there is no guarantee that it would be observed in other coordinate system. Today we shall consider, we shall define a tensor of higher rank. A tensor of rank P comma Q. That is, we have, if we consider an n-dimensional space, then we have n to the power P plus Q quantities which are defined as a I1, I2, IP. So it is a in the tensor which has P pth order contravariant indices and covariant indices JQ. The transformation properties is as alpha p. This is the quantities referring to the contravariant components, and then we have covariant indices. Beta 2 del J2 right up to del beta Q del JQ A bar alpha 1, alpha 2, alpha p, beta 1, beta 2, beta q. We can write it in a manner like this. This is del x I L del x bar alpha L with bar L ranging from 1 to P, M ranging from 1 to Q, del x bar beta M, del x j m, and then we have this part. A bar alpha 1, alpha 2, alpha p, and beta 1, beta 2, beta q. This is a mixed tensor of rank P plus Q. Coming back to the inverse relation or the reciprocal relation is that we write this one and this part will be interchanged. That is A bar alpha 1, alpha 2, alpha p, beta 1, beta 2 beta q is del x bar alpha L del x I L, then sum over m is equal to 1 to q del x j m del x bar beta m a I1 I2 IP j1 j2 jq. This is the transformation relation for a general tensor of rank PQ. Note that the first part is this P is the contravariant rank and Q, the second one, is the covariant rank. If we have a tensor of like this short, that the I1, I2, IL plus 1 or IL and IL plus 1 IP and similarly J1, J2 up to JQ. If we find that this is equal to a I1, I2, IP, IL plus 1, IL, J1, J2, JQ. Note that the interchange between the indices, this index and on the right hand side it has moved to this, and there is an interchange between the indices. It may not be at the interchange with the last one, but any two, if we have a tensor which is symmetric with respect to any two pairs of contravariant indices or any two pairs of covariant indices, this symmetry property is retained under coordinate transformation. But if we have a tensor which is symmetric with respect to the interchange of one contravariant and other covariant index, then this symmetry property may not be carried over to other coordinate system. So this is the definition of a general tensor. Now we shall go to what is known as proper tensor algebra, that is how to add two tensors, etc. Two tensors of the same rank can be added or subtracted. So if we have two tensors, addition, fraction of tensors of the same rank. This is very important. So we have two tensors. One is I1, I2, right up to IP, J1, J2, JQ. Another tensor is B, I1, I2, IP, J1, J2, JQ. Then if we then we may define a third tensor, or we may define a quantity C, which is the addition or subtraction between these two. Let me define quantity C. This is A, I1, I2, I3, J1, J2, JQ, plus or minus B, I1, I2, IP, J1, J2, JQ. Then this C, we demand that C will again be a tensor I1, I2, IP, J1, J2, JQ. How to prove this? Let us write this in terms of barred coordinate system. So if we write it in terms of barred coordinate system, this will be summation over L is equal to 1 to P del XIL del X bar alpha L then we have M is equal to 1 to Q del X bar beta M del X JM A bar alpha 1, alpha 2, alpha P, beta 1, beta 2, beta Q, plus or minus, similar thing, L is equal to 1 to P del X IL del X bar alpha L, M is equal to 1 to Q del X bar beta M del X JM B bar alpha 1, alpha 2, alpha P, beta 1, beta 2, beta Q. So if we write this as summation over M is equal to 1 to P del X I L del X bar alpha L summation over M is equal to 1 to Q del X bar beta M del X JM. Then we have A bar alpha 1, alpha 2, alpha P, beta 1, beta 2, beta Q, plus or minus B bar alpha 1, alpha 2, alpha P, beta 1, beta 2, beta Q. If we define it as C bar alpha 1, alpha 2, alpha P, beta 1, beta 2, beta Q, then we see that C and C bar are the components of a tensor or of rank P plus Q. P plus Q. So if we add two tensors of the same rank or subtract two tensors of the same rank, the resulting quantity is again a tensor, again belonging to the rank, same rank as the components. That is, we have, it is a tensor of rank P plus PQ, then this is also a tensor of rank PQ. C is also a tensor of rank 2. One thing, if we subtract tensor, subtract A from itself, then we get a tensor whose every component is 0, and this is a null tensor, which results in a null tensor. Now we define the multiplication of tensor. The tensor, two tensor can be multiplied in two different ways. One is called the outer product and another one is called the inner product. We shall first define the outer product of two tensors. We consider an example. And you consider a tensor of ijk and another tensor whose transformation property is that del xi, del x bar alpha, del xj, del x bar beta, del x bar gamma, del xk a bar alpha beta gamma, and we have another tensor b, which say for example it is BLM, so its transformation property is del xl, del x bar mu, del x bar nu, del x m b bar mu nu. So this we have considered two tensors. One thing, note that none of the indices are common in both the tensors. Then we multiply a I j k b l m. What is the resulting quantity? We have del xi, del x bar alpha, del xj, del x bar beta, and then before writing this we pick up this one, del xl, del x bar mu, then we write this one, del x bar gamma, del xk, and then finally this is del x bar nu, del xm, and finally we have a bar alpha beta gamma, b bar mu nu. This part corresponds to the transformations of a tensor whose contravariant indices are I, J and L. So it is a tensor of rank, contravariant rank 3 and covariant rank 2. We have multiplied two tensors whose for tensor A the contravariant rank is 2 and covariant rank is 1, and for the tensor B it is a tensor of type 1, 1. So resulting quantity is a tensor whose contravariant ranks have been added up, 2 plus 1, 3, and the covariant rank has been added up separately. So this is called an outer product of two tensors. So we can define the outer product for two general tensor, but it will be complicated. In fact, that for outer product, if we have a tensor of rank P1, Q1, and we have another tensor B of rank P2, Q2, then the resulting quantity C will be a tensor of rank P1 plus P2 and contravariant rank P1 plus Q2, P1 plus P2 and covariant rank Q1 plus Q2, provided none of the indices are common in both the tensors A and B. Now we shall consider the same example to define inner product of two tensors. What happens to inner product? We consider again two vector or two tensor of the same kind, but this time we allow a repetition of indices. So we define what is known as inner product. We have the indices I, j and k for tensor A, and for this tensor we define we change this, and I denote this change in red color, say j, and so it will be j. Again, we have two tensors, but the problem is that one contravariant rank of one tensor is equal to the covariant rank of the other tensor. So what we get as a product? So we write A, I, J, K, B, L, K. So the thing is that del xi, del x bar alpha, del xj, del x bar beta, del x bar gamma, del xk, then from this del xl, del x bar mu, del x bar mu, then we have del x bar nu, del xj, b bar mu nu. We couple these two terms. So we have del xi, del x bar alpha, del xj, del x bar beta, then del x bar nu, del xj, del x bar gamma, del xk, and this term del xl, del x bar mu. One thing I have missed here is the A bar alpha beta gamma. This was missing, sorry. So this is A bar alpha beta gamma b bar mu nu. What is this quantity? When we summed over j, the repeated index j, there is a repetition of indices. So according to Einstein's summation convention, there is a sum over j, and this results in delta bar nu beta. So if we write this, then the resulting quantity becomes del xi, del x bar alpha, del x bar gamma, del xk, del xl, del x bar mu, and here we have A bar alpha beta gamma, B bar mu will be replaced by beta. This is the transformation. This property is being, this is the transformation law for a tensor having covariant rank 2 and contravariant rank 2 plus 1 tensor. So what happens is that the resulting quantity, instead of being in the case of outer product, the outer product, the covariant rank of two tensors are being added up, and the contravariant rank is again added up separately. In the case of inner product, if if we have two tensors of which one has a covariant contravariant rank which matches with the covariant rank of the other one, then the rank of the tensor gets reduced. In this case, the contravariant rank was, when added up, was 2 plus 1, and this is being reduced by 1, so that the resulting quantity has this. And if we consider the covariant rank, it is 1 plus 1, and it is reduced by 1, so it is 1. So it is a tensor of rank 2 plus 1. In general, if we have two tensors, one of rank P1 and other one is rank P1, Q1, another one of tensor rank P2, Q2, of which one, say L covariant ranks, covariant indices of L, there is a L common pair of covariant and contravariant. So there are L quantities, L covariant contravariant indices of this matches with the covariant index of the second, or vice versa. Then we have it on inner product, we get a tensor whose contravariant rank will be this, and the covariant rank will be, so it will be reduced. If we take one contravariant vector and another covariant vector, then the resulting quantity is a tensor of rank 0 by 0, that is, it would be a scalar. Another thing is which is very closely related to this inner product is the contraction. The basic difference is that when we multiply two tensors having some common indices, covariant and contravariant indices between two tensors, then we speak of inner product. Another thing is that we may have a tensor, a single tensor A. We have obtained the tensor A by somehow, and of which we have a repetition of indices. Say this is I. So in that case, we have, this is the transformation relation. And if we couple these two and sum over I, the resulting quantity will be delta bar gamma alpha del xj del x bar beta a bar alpha beta gamma, which is, since gamma is equal to alpha, this will be del xj del x bar beta a bar alpha beta alpha. This is the transposition property of a tensor of rank 1, 0. This is, so we had initially a tensor of rank 2, 1, and of which one covariant indices and one contravariant indices are same. So we have a reduction of rank. This rank is reduced from 2 minus 1 to 1, and this from 1 minus 1 to 0. This is known as contraction of a tensor. conclude this discussion, we finally define the reciprocal of a rank 2 tensor. We consider a rank 2 tensor which is most conveniently represented by a matrix. We have a real tensor, say Aij, tensor of rank 2, then this is being represented by a matrix, say A11, A12, etc. In a dimensional space it is A1n, A21, A22, A2n, AN1, ANN. This is the matrix representation for this rank 2 tensor. We may define the cofactor tensor. Cofactor tensor can be defined as usual. Yes, this is A11, A12, A1n, then finally AN1, ANN. This is the cofactor tensor, and if we take the conjugate of it, then we get adjoint tensor. Adjoint tensor is like this. A1n, this is the adjoint tensor, and reciprocal of E tensor Aij is defined as det A, this is the determinant of A times the adjoint tensor of A. If we find the adjoint of a contravariant tensor, it would be a covariant tensor. So the product of a contravariant tensor of rank 2 with a covariant tensor of rank 2 having the same indices leads to a scalar. That is to say, if we call this reciprocal tensor as a Bij tensor, then in matrix notation we used to write Aik Bkj is equal to delta Ij, because B is the reciprocal of A. This is what we write in matrix notation. In tensor notation we write it Aik Bkj is equal to delta Ij. This is what is known as the reciprocal of a tensor, reciprocal tensor. So a reciprocal tensor of a rank 2 tensor is, if we represent the first tensor as a matrix, then the other tensor is the inverse of the matrix. And if we start with the contravariant tensor, then its reciprocal is a covariant one, and vice versa. This is a brief outline of the tensor algebra. In the next lecture, we shall take up the case of quotient law, which is found to be very important in connection with the tensor analysis.